let's understand the layout of the screen. The numbers in the upper left will be referred to as the dataset and are the values which will be used in all our calculations. The graph in the bottom portion of the screen shows each number's position on the number line. For example, the number 55 is located here on the number line, and it follows that each of the numbers has a position that corresponds to the value of the number. Let's turn our attention to the mean. It is a measure of central tendency. It is a number at the arithmetic center of the dataset. This is the equation used to calculate the mean. The Greek letter mu is used to represent it. The uppercase Greek letter sigma followed by x is read as the summation of x. It is simply the total of all the values in the dataset. N is the number of values in the dataset. Let's now calculate the mean. The members of the dataset are rewritten here in a column. The summation of these values is equal to 315. N is the total number of values, which is 9 for this dataset. The mean, or mu, is equal to 315 divided by 9 for a result of 35, which we will copy in this location also. Its location on the number line is indicated by the larger red dot. Let's further our understanding of the mean by observing the impact the values in the dataset have on the mean. If a member of the dataset were to decrease in value, the sum of the x values would correspondingly decrease. The mean will also decrease, and its position on the number line moves to the left. In fact, if any member of the dataset were to decrease, it would decrease the value of the mean, and its position on the number line would move to the left. Conversely, if any member of the dataset were to increase in value, the value of the mean would increase, and its position on the number line would move to the right. Let's examine the standard deviation, which is a measure of the diversity, that is, how diverse the data is from the mean. This is the equation to calculate the standard deviation. Now let's discuss each of its parts. The term in parentheses is the difference between each value in the dataset and the mean. This quantity is then squared. We then find the sum of these squared values for all the values in the dataset. Then divide the sum by n, the number of values in the dataset. Finally, the standard deviation is the square root of this result. We use the Greek lowercase letter sigma to represent this quantity. Let's now calculate the standard deviation for our dataset. First, we determine the difference between each x value and the mean. From the first value of x, 15, we subtract the mean, which is 35, for a result of minus 20. Then, from the next x value, 20, we subtract the mean of 35 for a result of minus 15. This procedure is repeated until we have a result for each value in the dataset. The next step is to square each of these values. That is, minus 20 squared is 400. Minus 15 squared is 225. And so forth until the square of each of the differences with the mean is calculated. Now we sum all those squared values for a result of 1500. Now we need to divide the summation by n, which we said earlier is 9. Therefore, 1500 divided by 9 is 166.67. The final step in calculating the standard deviation is to take the square root of the 166.67 for a result of 12.91. We will also copy the value of the standard deviation here. The standard deviation is often referred to by its Greek name, sigma. As we did with the mean, let's now vary the values of the dataset and try to gain some insight into the characteristics of the standard deviation. Let's first decrease a member of the dataset. As the value of a member moves towards the mean, as shown by its position on the number line, its difference with the mean becomes correspondingly smaller, making the square of the difference smaller, and ultimately resulting in a smaller value for sigma, the standard deviation. Let's point out that sigma is becoming smaller, not because the x value is decreasing, but because its distance from the mean is decreasing. This is the case for any of the values in the dataset. As it moves closer to the mean, its distance from the mean decreases, and ultimately causes sigma to decrease. Each data member's contribution to sigma is not its value. It is the distance each value is from the mean that contributes to the value of sigma. Even if the values to the left of the mean increase, their distance from the mean decreases, decreasing the value of sigma even further. Conversely, as data values move away from the mean, their distance from the mean increases, and the value of sigma increases. If all the data values were to converge towards the mean until they all equal the mean, the standard deviation becomes 0, because their distances from the mean becomes 0. When they move away from the mean, sigma becomes larger. Let's look at one more example to illustrate the idea that the standard deviation is a measure of how spread out the data is. If the values were to change in unison, the value of sigma will not change, because their distance from the mean is not changing. Notice that x values are changing, and as a result, the mean is changing, but their distances from the mean are not changing. Another concept we will be using in subsequent videos is that of relative standing, which is also known as the z-score, and is calculated using the equation shown. Each x value has its own z-score. It is found by subtracting the mean from the x value, then dividing that result by sigma, the standard deviation. We begin by subtracting mu, the mean, 35, from the first value of x, 15, for a result of minus 20. Then divide minus 20 by the value of sigma, 12.91, for a result of minus 1.55. For the second x value of 20, we subtract the value of the mean, 35, for a result of minus 15. We then divide the minus 15 by sigma, 12.91, for a z-score of minus 1.16. We repeat this calculation for each of the x values until we have a z-score for each x value. The x values are now plotted based on their z-score. Because the z-score is the distance that each x value is from the mean, divided by sigma, the standard deviation, the z-score is the number of sigmas or standard deviations the x value is from the mean. A negative z-score indicates the x value is to the left of the mean, and a positive z-score indicates the x value is to the right of the mean. And 0 always indicates the location of the mean. The x value of 15 has a z-score of minus 1.55, and is located 1.55 sigmas to the left of the mean. For an x value of 55, the z-score is a positive 1.55, and is located 1.55 sigmas to the right of the mean. Each of the x values in the dataset has a z-score, its distance from the mean, measured in standard deviations, or sigmas.